All right, so I'd like to talk about Chapter 15, Acids and Bases. So these are some binary acids, and you should be familiar with some of these, like hydrochloric acid or hydrofluoric acid. So you're going to use the hydro, remember for the naming, you're going to use the hydro in front for those. Those don't have any oxygens in them. So those are the binary acids. But then you have the oxy acids. So remember these, you don't use the hydro. We have the sulfuric acid based on the sulfate, SO4 2-, you're going to need 2 hydrogens, so that's sulfuric acid. And then nitric acid, nitrate is one of the polyatomic ions. It has a -1 charge, so you put 1 hydrogen on there to balance it out. These are the oxy acids, and these have hydrogens on them. But notice in the naming, you don't have the hydro in front. All right. So carboxylic acids have this group, C double bond O, O, and then an H at the end like that. And you find these carboxylic acids all over, like citric acids here. You find them in apples, you find them in oranges, you find them in grapefruit, like things like that. So only this hydrogen is acidic. So if you write down the formula here, only this H is acidic. This is not. These other ones are not acidic. These hydrogens here, just the first hydrogen. So they always put the acidic hydrogen first there, just to indicate how many acidic hydrogens does it have. This one actually has 3 acidic hydrogens. All right, so we're going to define acids and bases based on 3 different definitions: the Arrhenius definition, the Bronsted-Lowry definition, and then the Lewis definition. So the Arrhenius definition is based on acids making H+ ions when you put them in water, or hydroxide ions when you put them in water. So that's going to be the first one. And then Bronsted-Lowry, they talk in Bronsted-Lowry definition, they talk about transferring H+ ions, and the Lewis definition, we talk about electron pairs. We'll get more into that. Here's the Arrhenius definition. Basically, what it tells you is whenever you put an acid in water, it makes these H+ ions. And that's how you know you have this acid, because you make these H+ ions. So that's an Arrhenius acid, just like when you put HCl in water. Remember, HCl is a strong acid and it completely dissociates. So it completely breaks up into acid H+ and Cl-. But when we say H+, note that we're actually, in fact, mean the hydronium ion. Is just a shortcut. When we say H+, we actually mean this one, because that's how it actually exists in nature. So water binds that H+ ion and makes this hydronium ion, which is the H3O+. So that's what you actually see, but you often see it written just H+. That's just shorthand. We really always mean H3O+, the hydronium ion. Now, what about Arrhenius definition of a base? A base, when you put in water, produces the hydroxide ion, the OH-. This should have a minus there. So hydroxide ions for bases. So NaOH, sodium hydroxide, is a strong base. When you put it in water, it completely dissociates into sodium and hydroxide. Okay. Whenever you react an acid and a base, you end up getting water and a salt. Right. So the way you can think about it is this H+ and this OH- combine together to give you a water molecule. And it's actually an exothermic reaction. It produces heat when it does that. So you'll see that it heats up. So here we're making sodium chloride and water with an acid-base reaction. All right, so Arrhenius theory, I mean, basically defining acids based on Arrhenius theory. It doesn't explain other substances like ammonia, for example, or some other ionic compounds that don't make the hydroxide ion. but act like bases. So there's some that act like acids but don't necessarily make H plus ions, and some that act like bases and don't necessarily make the OH minus ions. So we need they needed to make a better definition. Okay, so we have the Bronsted-Lowry acid-base definition here. And in this definition, an acid is a proton donor and a base is a proton acceptor. Right. So that's a little different than before. So it doesn't matter whether it makes OH minus in solution or H plus. The acid donates the proton and the base accepts it. So let's look at an example here. Here we have an acid, HA. A could be anything, but the H is the acidic hydrogen, and it's going to donate that acidic hydrogen to B here. And so the acid is the proton donor here, and then the base is here, the proton acceptor. So it has actually an unshared pair of electrons which can accept that H plus ion, and then it becomes HB plus. So, and then you have this A minus here. So the Bronsted-Lowry definition defines it in terms of donating or accepting a proton. Okay. So when you have an acid-base reaction, in this case like HCl and water, HCl is the acid and it's donated a proton to water. But now water, normally we would think of water as neutral, but in this case, water is acting as a base because it's accepting the H plus ion. So in this case, water is acting as a base. So it's not always just identifying which one looks like a base and which one looks like an acid. Water is not normally a base. It could be either a base or an acid. But normally we think of it as neutral. But here it's accepting the proton, so it's acting like a base, right? So basically we say water is acting as a base, HCl is the acid. And so if it can donate the proton, it's the acid. If it can accept it, it's the base. And that's what we're looking for. Now, what about ammonia? Ammonia is NH3. No, it's different than ammonium, which is NH4 plus. In this case, we're going to look to see which one is donating. Well, it looks like water is donating a proton to NH3, and it's becoming NH4 plus, and then water is being left with a hydroxide. So the NH3, the ammonia, is the base, and water this time is acting like an acid. So it turns out water can either act like an acid or a base, depending on whether it's donating or accepting a proton. You just have to look to see which one is giving away the proton and which one is accepting it. The one that's giving away the proton is the acid. The one that's accepting it is always the base. And that's based on the Bronsted-Lowry definition. So water, in this case, acts like a base, accepting the proton, but in this case, acts like an acid, donating the proton. That's called amphoteric. That means you can act as either an acid or a base. So if it could either accept a proton or donate a proton, it's going to be amphoteric. It can act as either one. So with the Bronsted-Lowry definition, you can actually have reversible reactions. So we talked about how not all reactions just go to completion. Sometimes you reach a kind of equilibrium between the reactants and the product. So in this case, HA is the acid and B is the base, accepting it. But if you look at the reverse reaction, this one is the acid and this one's the base. So in terms of the reverse reaction, it's going to be a little different, right? You're going to have to look at which one's accepting the proton, it's going to be this one, and which one's donating, it's that one. So it's going to be the reverse. And so we can write reversible reactions using the Bronsted-Lowry definition. And what do we call the one on the right? Well, if the one on the left is the base, the one on the right is the conjugate acid. Why is it the conjugate acid? Because when you look at the reverse reaction, it's acting like an acid now. So the base always on the right side becomes a conjugate acid. And if it's an acid on the left, it becomes a conjugate base on the right. And that's called the conjugate pair. So that's making a conjugate pair. So ammonia and ammonium are a conjugate acid-base pair. Okay, and they differ by a proton, the conjugate acid-base pair. So here, hydrofluoric acid is the acid. It's donating the hydrogen to the water, which is the base, and it's making the hydronium ion and the fluoride ion. So in this case, this is the acid, but this is the conjugate base here. We call this, over here it's the base, it's particularly the conjugate base. And then here's the base, and here's the conjugate acid on the right. And it's a conjugate acid-base pair. So the acid becomes a conjugate base, and then the base becomes a conjugate acid. What about an ammonia here? Ammonia is the base, it becomes a conjugate acid. Water is acting like an acid because it's accepting, it's actually donating the proton, it's acting like an acid, so it actually becomes the conjugate base here. So because if you look at the reaction going from right to left, it's the hydroxide that's going to be accepting the proton, and ammonia is going to be donating it going from right to left. And so this one's acting like an acid, this one's acting like a base, but because it's on the right side, we call it the conjugate acid and the conjugate base. Okay, so here we have the acid, HBr, and then the base is water. So this one's the acid, right? And then this is the base. And then here would be the conjugate acid. And then this would be the conjugate base here. Because in the reverse reaction, it would be the opposite, right? This one would be the acid and this would be the base. So let's look at this one here. So if you want to determine which one's the acid and which one's the base, well, let's look at how many hydrogens this has. This has an NH2 and then it goes to NH3. So accepted a proton. This one donated a proton. So this one's acting like an acid. And this one's acting like a base because it's accepting the proton. Here it becomes the conjugate acid though, and over here it's the conjugate base. Okay, so write the conjugate bases of each acid. So if this is an acid, HCO3 minus, the conjugate base, acids, remember, have to donate the proton, so it's just going to be CO3 2 minus, because you're going to remove the proton, and for this one, it's going to be ClO2 minus, right? Write the conjugate acids of each base. This should say H2, so that's a typo there. H2PO4 minus, because H3PO4 would not have a charge. And then the conjugate acid would be H3PO4. And for this one, it would be H2SO4. Right, so if this is a base, once it accepts a proton, it becomes H2SO4. Okay. Now strong acids, they completely dissociate. So virtually 100% of the acid molecules ionize. And if you have HCl, for example, you put in water, it makes the H3O plus and Cl minus. You use a single arrow to indicate complete ionization. So you don't have a reversible reaction in this case. It just completely goes and makes product entirely. So that's the strong acids. It's important to know the strong acids. These are the strong acids here. There's 6 of them: hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric acid. So these are very strong acids. Those are the ones that are very common and the ones that are used a great deal. All right. What about weak acids? So those are the strong acids. If it's not a strong acid, you could assume it's going to be a weak acid. Hydrofluoric acid is a weak acid. It only partially dissociates, and it only makes a little bit of the H3O plus. So if you have a lot of HF, here, hydrofluoric acid, you're going to get a little bit of H3O plus, a little bit of F minus, but not a lot. Usually it's actually less than 5%, so it's not very much that dissociates. And so when you put it in water, it's still going to make H3O plus, so it's still an acid. So if you wanted to draw this out with arrows and show which way it's going to go mostly, it's mostly going this way actually, and only a little bit dissociates to the right. But if you draw the double arrows, that's fine. In this case, only a small amount is going to go to the right. So that means that the concentration of this one is going to be a lot less than the concentration of this one. And that's because very little is going to go and make the H3O plus. But it's still going to make some, so it's still going to be an acid. So let's look to see. When we have a general acid, just like we had hydrofluoric, we're going to use A here to represent anything here. It could be anything. It could be fluoride, for example, so hydrofluoric. And then it makes the H3O plus, A minus. So that this is your acid, and water is acting as a base, accepting the proton. And then you have the reverse reaction, which is H3O plus and A minus going back to the original. If we want to write it in shorthand, we can do it this way, which is just HA going to H plus and A minus. So that's just like a shorthand way of writing it. And then we can write what the Ka is, right? It's always going to be the products over the reactants, but we don't include water in the equilibrium constant because it's a pure liquid. So whether you write it in terms of the top reaction or the one underneath it, we're talking about the same thing. It's just here they're using shorthand. They're calling it H plus instead of H3O plus. This is the more accurate way, but this is the shorthand way if you wanted to write it really quickly, right? So we're going to have, just like we did before, we have the equilibrium constant, concentration of the products, raise the coefficient, in this case, 1 over A, so that's called the acid ionization constant. It's just the equilibrium constant we talked about before, or except it's applied to acids. So we can look at the different Ka values, like here, and it's a K1.1. Okay, and so we have hydrofluoric acid, and it keeps going on. So notice that these Ks are large up here and down here. Kas are very small, 1.3 times 10 negative 10. That means that very little product is being made. This is a phenol or hydrocyanic acid here. You make very little product. So they're very, very weak acids in that case. So we have the Ka values. You could always look up the Ka values if you need to in this table, 15.5. Now, what about water? Water amphotericity. And in fact, when you just have one of them will act like an acid and another water molecule and some concentration of hydroxide. This is water itself ionizing and making an acid. One of them is acting as an acid, the other one's a base. It doesn't matter which one because they're identical, right? It's just that one of them is donating the proton and one of them is accepting it. And over here you have the conjugate acid and the conjugate base. So the point being that you're going to have some concentration of hydronium ions and hydroxide ions even in pure water. And in fact, we can actually calculate that, because for pure water, the hydronium ion concentration and the hydroxide ion concentration are both 1 times 10 to the negative 7. Notice, based on the equation, for every time you make the true, not if you have an acidic solution or a basic solution, it's going to be different then. So, right, if we have the equilibrium constant, when we write the equilibrium constant, we don't include the pure liquids, but we do include these two. So if you multiply these two together, that will give you the equilibrium constant for water, which we call Kw. The ion product constant, Kw for water, is 1 times 10 to the negative 14. And each one of these is 1 times 10 to the negative 7. So when you multiply them, you get 1 times 10 to the negative 14. And so that's going to be true, so that if you increase the HCl plus concentration, OH minus must decrease. So now we can consider cases where we're no longer in pure water. If we add more acid, then some of the hydroxide is going to be consumed. One might go up, the other one go down, but this constant actually stays the same. It's just still going to be 1 times 10 to the negative 14. Okay. So all aqueous solutions have both the hydronium ion and the hydroxide ion. If it's neutral, we know that the concentrations are both 1 times 10 negative 7. But if it's acidic, then the hydronium ion concentration is going to be greater than the hydroxide ion concentration. And so it's going to be greater for the hydronium, less for the hydroxide. But basic solutions are going to be the opposite. The hydroxide ion concentration is going to be greater than the hydronium ion concentration. But what's true is if you multiply both of them, you're still going to get 1 times 10 negative 14. That's our Kw. It's just those concentrations will change. So calculate the hydronium ion concentration at 25 degrees when the hydroxide ion concentration is 7.5 times 10 negative 9 molar, and determine if the solution is acidic, basic, or neutral. So we know what Kw is. Let's go back. Let's look and see here. So okay.